All right, so for our final chunk for this section, I know there's a lot in here, but there's so much to unpack and so many different applications with this fundamental theorem that it's just a lot to cover. So the last thing we're going to do is another extension or another application of the fundamental theorem of calculus, but it's called the second fundamental theorem of calculus. This is a really big important one, and another way that derivatives and integrals interact or a linkage between them. But before I just straight up tell you what it is, I want to explore and show you guys a few things, okay? So for this first one, I'm going to let f of t be the function 2t plus 3, okay? So one thing to keep in mind that inputs for functions really don't matter. We've always traditionally used x as the input, y as the output, or f of x as that notation for the value of the function. But realistically, it doesn't matter what variable I use to represent the input. It still does the same thing. If it says f of q, f of b, f of t, it doesn't matter. It's a variable. We can substitute a value into the function and pass it into the pattern and evaluate it. So for these problems, you're going to see t's used a lot. And the real issue is that the variable of integration, this guy, t in this case, has to match up with the variable used in the actual function expression. But what we're going to see here, all of these examples use variables in our bounds of integration. And there's a particular reason why and how that interacts with the whole process. But the rule for these is that this variable can't be the same thing as what's inside the integral. So a lot of times we want the integral variable in the bounds to be x, so we just pick something else. It's arbitrary. The most commonly used one is t. That's why it shows up in all these examples. But realistically, it doesn't matter what the variable is as long as it's not the same as this guy, okay? All right, so all that said, for part A, we're told to find what the integral from 1 to x of 2t plus 3 dt is equal to. Okay, well, we saw an example earlier where we had a problem like this where there was a k sticking up here in this spot, but they told us what that integral's value is equal to, so then we could just take that final equation and actually solve for that missing value of k. So this is just like that problem. I just haven't given you a value that the integral is equal to. So at the end, there's nothing really to solve. We just end up with a new expression. So we're going to treat this just as we would any other fundamental theorem of calculus problem. But in the end, we're not going to come up with just a number, okay? So if I have the integral from 1 to x of 2t plus 3 dt, I would integrate, find my antiderivative. So integral of 2t is t squared, integral of 3 is 3t, and then my a and b values, so 1 to x. So f of b means x goes in for t, so that would produce x squared plus 3x. And then f of a would be 1 going in, so that would give me 1 plus 3. So in the end, the final value or expression that this is equivalent to would become x squared plus 3x minus 4. So that is our final answer. Now, what part B is asking us to do is to take the derivative of this integral. Well, we just found out, or just stated, that this integral is equivalent to this expression that uses x. And since that variable matches up with the variable that I want the derivative with respect to, it makes sense to use this guy to make a swap. So instead, I am taking the derivative of x squared plus 3x minus 4. So when I do that, I get a final answer of 2x plus 3. So I want you guys to look at that and think about what it is that we just did and how this guy compares to what we started with, okay? So think about that for a second, and now we're going to try the same thing again, but with a different function. So for this one, g of t is 3t squared minus 6t plus 5. First, I'm going to integrate from 3 to x, g of t dt, okay? So I use the function name that time instead of the actual expression, but it really doesn't matter. So when I integrate that, if I integrate this function, that becomes t cubed minus 3t squared plus 5t. And then, again, I'm going from 3 to x. So when x goes in, that produces x cubed minus 3x squared, oops, came in too soon with that parentheses, plus 5x for my f of b part, and now f of a is going to be 27 minus 27 plus 15. So all in all, the 27s cancel, so I get that this integral is equivalent to x cubed minus 3x squared plus 5x minus 15. Okay, so now for the second part, now we will take the derivative of that result. Again, we're taking the derivative of the integral that we started with, but that integral is equivalent to this expression. So because of that, when I take the derivative of this guy, I get 3x squared minus 6x plus 5, and the constant disappears. So again, think about how that result of this kind of two-step process compares to what we started with. Well, hopefully, after looking at those two, you guys notice some kind of pattern. Hopefully, you notice that the structure of this resulting expression is identical to the original function. The only difference is we switched inputs. We went from an expression that depended on t to now it's the exact same expression that depends on the new variable x, which came from our integral. So what really happened here is when I integrate and go backwards, I take all of this stuff and I integrate it using the regular power rules because this variable matches up with the variable of integration. So there's no difference in integrating 3t squared versus 3x squared. As long as the variables of integration match up, it's still the same math. But when I go to evaluate it, f of b and f of a, f of b turns into the exact same expression, but with x's plugged in there, and then the f of a is just some constant. But when I immediately after that take the derivative, that constant disappears, and all the other terms revert right back to what they were before, but now they have x's in there. So because of that, if I were to try and use this same kind of process with this result, if I skip over the first step, I know that if I integrate j of t using whatever integration or antiderivative rules I need to use, I'm going to get an answer. And when I do my fundamental theorem, I'm going to stick x's into all those things. But then when I take the derivative of those, they're going to turn right back into what they started with, but now they will all be functions of x. The a part, when I plug that into the antiderivative, I just get a number because a is a constant. And when I take the derivative of that number, it always turns into 0. So it's just going to disappear. So because of that, what we kind of establish here is a rule. The derivative with respect to x of any integral from a constant to x of some function j of t, doesn't really matter what the function is, that final result is really just that same function, but it now uses x as its input. That's it. That's what we've just discovered here with these couple of examples, that this now becomes the new input because I know that integrating takes me a step back, but then differentiating pushes me a step back forward. So we actually end up right where we started. The only difference is that input variable has now jumped in there. Okay? All right, now let's try to take it a step further. So now k of t equals cosine of t. So that's my new function. But now my integral is going from 6 to 2x squared. Okay? So we're going to start this off, pretend like we didn't just discover some kind of rule, and try it from the same kind of process. So if I integrate cosine of t, that yields sine of t. And then I'm going to go from 6 to 2x squared. So my f of b turns into sine of 2x squared minus my f of a would be sine of 6. Well, there's not really a way for me to simplify any of that, so I just get sine of 2x squared minus sine of 6, whatever that number is. Okay, well, if that's what that integral is equivalent to, for the second step, when I go to take the derivative of that, I am taking the derivative of this expression. Well, for the first guy, that is sine of something. So its derivative requires a chain rule. So if I start with sine of u, where u is 2x squared, and then u prime would be 4x, so then the derivative of sine of u would become cosine of u times u prime. So if that's the case, then in this case, when I take the derivative of this expression, I'm going to end up with 4x times cosine of 2x squared, and then minus sine of 6. Well, remember, sine of 6 is just a number, so the derivative of that number, again, just disappears. So this is all I'm left with. So that is the derivative of this integral. So again, I want you to think about how this final result compares to the starting value. But in this case, I want you to take into context the actual integral that we took the derivative of as well. Okay, so think about all that. Now let's try another one. Okay, my function L of t is equal to e to the t power, and I'm going to find the value of the integral, or an equivalent expression for the integral from 3 to cosine of x of L of t dt. Okay, well, L of t is e to the t power. The derivative, or excuse me, integral of e to the t is e to the t. So we're going to go from 3 to cosine of x, and that would yield f of b would give me e to the cosine of x power. Actually, I don't need parentheses here. Minus my f of a would be e to the third. So there's my equivalent form. Now we'll take our equivalent form, take the derivative of it. So derivative of e to something, again, this is another chain rule. So e to the u, where u would be cosine of x. So then u prime would be negative sine of x. And the derivative of e to the u is e to the u times u prime. So that results in negative sine of x times e to the cosine of x power. And then derivative of e cubed, well, e cubed is again just a number, so the derivative of a constant is 0. So this is all that is left. So if you really look at the main difference here, so the biggest difference between these integrals and the first set are where that variable x was in the first guy, now it's some kind of other weird function of x. So 2x squared has a different derivative than just x because it's a higher degree power rule with a coefficient. So that's where the derivative of 4x came from. But then this one, cosine, it has a different derivative than just x because it's a function of x. So what you guys hopefully noticed or figured out here is that when that upper bound is not just x, but it's some other kind of function of x, this will actually require us to use the chain rule. Both of these examples here, where we had some function of x or some kind of u in that upper bound spot, both required us, when we went to take the derivative, to use the chain rule. We had to come up with our u stuff. So what does that mean? Well, let's take a generic one. So let's say that I wanted to jump straight to the answer of what's the derivative with respect to x of an integral that goes from some number a to some function g of x of f of t dt. Well, we still had the same kind of idea as before, where we take this thing and it shows up as replacing the input spot of what used to be here. So this used to be e to the t, and now it's e to the cosine of x. But the difference is we have this extra thing that's being multiplied. In this case, it was negative sine of x. Up here, 2x squared did become the input instead of t. Now there's 2x squared there. But then we also, again, had that extra 4x. Well, the significance of both of those extra factors is it was the u, or excuse me, the u prime of our u when we went through this process. So that is the big takeaway. So this shortcut, or this rule, says that this final result should end up being f composed with g of x. So we take this guy and we stick it in there for the old input, but I also then need to multiply by the derivative of this upper bound. So we need to multiply by g prime of x. That, in a nutshell, is the second fundamental theorem of calculus, which says that if f is continuous on an open interval I, then for all values of x in the interval I, the derivative with respect to x of the integral from a to u, where u is some function of x, like cosine of x or 2x squared, of f of t dt, then that result is equal to f of u times u prime minus f of a times a prime. Now, the only reason we wrote this out in a different way than what we just talked about was there are some instances where this bottom guy may actually end up being some other function of x as well. We're going to look at an example of that in a second. But if it is just a number, well, that a prime then, this guy is just 0, which means that whole term just disappears. So then we are, in fact, left with just this guy. But it is a good habit to at least remember that second part, just in case we do end up with a crazy extra little function down there, okay? So now that we know this shortcut, let's try a couple of these, okay? So derivative with respect to x of the integral 3 to 3x minus 2t squared, okay? Well, second fundamental theorem says that we are going to take this guy, stick it in here for t, so we now have 3x minus 2 raised to the second power, but then we're going to multiply by the derivative of this guy, which is just 3. That's it. That's my answer. I know the second part, we can write it out, okay? If we were to write it out, then we would get 9 times the derivative of 3, which is 0. So it's not necessary for us to write that out. Again, that second piece, is as long as that other integration or bound of integration is a number, that part of this rule will always end up being 0. So if you really think about this in a nutshell, this is basically very similar to our fundamental theorem of calculus. So fundamental theorem of calculus is just the integral from a to b of f of x dx is equal to the antiderivative of b minus the antiderivative of a. But the main difference here, it's twofold. First, because I'm taking the derivative, I don't go back to an antiderivative. I'm taking the derivative of the antiderivative, which is this same function. So that's why we don't change back to capital F. It's still little f. The second main piece is now that new substitution, that u is going in to make the new. And so instead of b and just getting a number, it's some kind of function of x, u, and then we have to make sure that we multiply by that u prime. All right, let's try a couple more. So a couple different variations of this, but again, the rule still follows. So this is a little bit different notation as well. So this one says, I'm actually going to make it a function. So there are ways, and we're going to dive into this a good bit more here in a second. I can actually name a function and set it equal to an integral. And we'll get into what that means, but for right now, let's focus on the how we handle or work with that. So if I say that capital F of x is equal to the integral from x to x cubed of cosine of t dt, and I want the derivative of this guy, well, okay, notationally, derivative of capital F is capital F prime. We could revert back to the little f, but we're going to stick with capital F for right now. But now I need to take the derivative of this. So again, the derivative of an integral turns into the function inside f of u times u prime. But in this case, the bottom guy is also a function. So instead of thinking it as f of a times a prime, let's think of it as f of v times v prime. So wherever you have a function of x rather than a number, you will have an f of u times u prime kind of quantity. So again, if we were to go backwards, we would integrate cosine becomes sine, then I have to stick x cubed in there, then I have to stick x in there, then I take the derivative of both of those. The sines turn back into the cosines, but now they have their new arguments, and then because of the chain rule, we'd have to multiply by those derivatives as well. So that's why we can always just jump straight to this result. So in this case, this would become 3x squared times cosine of x cubed, okay? So that's my f of u is the cosine of x cubed, u prime, I just moved it out in front, and then minus cosine of x, there's my f of v, but then in this case, x, its derivative, or the v prime is just 1, so you can write that, but it's not necessary. So that is our final answer. All right, let's try another one. Now, this one's even more strange because we're starting from a function of x and going to that constant. So this one's a little trickier. So this one, if you were thinking about it in terms of this rule, this is actually going to be f of b times b prime minus f of u times u prime. So this is a little backwards because normally it's a number to a function, but now it's backwards. So this first guy, that part's actually going to turn into 0. So we're going to end up with 0 minus our result. So whenever this happens and we have this function down here at the bottom, we will end up with a negative result out in front. Okay? So in this case, our capital F prime would be, I know it's going to be negative, because again, this result, but now we're going to stick 2x minus 1 in here for y. So that does become a little hairy, so let's do this off to the side. So I'll have 3 times 2x minus 1 plus 7. That's all inside my argument. So it becomes 6x minus 3 plus 7, or 6x plus 4. That is the new argument. So we get negative sign of 6x plus 4. Of course, now my tablet's going to freak out. But then again, we have to multiply by our u prime. And be really careful. It's really easy to look at this and say, oh, well, I'm going to take the derivative of this inside. Well, that's not the case. I'm taking the derivative of u, the thing that I substituted into that argument to create that thing. So in this case, my u prime is 2, not 6. So be very careful. So I can move that 2 out in front, so we'll write this as negative 2 sine of 6x plus 4. That is our derivative. All right. Now, you may be asking yourself, why did we go through all of this? Why is it a big deal? Why do I need to know how to take the derivative of an integral? That seems kind of counterintuitive or unnecessary because they're opposites and they seem to just be canceling each other out in a sense. Well, the reason why is because of examples like these two, where we set a function up and define it as an integral. Or another term for that is an integral defined function. Or I like to call them accumulation functions. So that is one really big application of the second fundamental theorem of calculus. It allows us to define functions that depend on the value of an integral. For example, let's say that g of x is equal to the integral from 2 to x of f of t dt. So what that means is because the function of g of x is defined as an integral, we can call it an accumulation function. And this set of information is true. So when we define a function this way, the output values of the function g of x are actually equal to the area under whatever function is inside of that integral, or in this case, the f function, or f of x. Now, that function inside, when we look at its graph, it would still be graphed on an xy coordinate grid. But again, the variables inside of the integral can't use the same input as the upper bound for the integral. That's why we just pick something arbitrarily like t. So we can change that. It's not that big of a deal because when I pick a value of x, that value of x will now determine how much of the area of f we're going to accumulate. So as that value of x fluctuates, we're going to accrue or accumulate more and more area under the graph of f. And so the output of g of x changes as well. Another important piece, the output values of g can also be interpreted as the total amount of change to the antiderivative of f of x that has accumulated over that interval of 2 to x. So what this does, this actually adds an extra type of interpretation to our series of functions. So up until this point, we have worked with functions f, f prime, f double prime, where each one of them tells us some kind of important piece of information. So if I start with my original function f, that's like telling us about position. So if I say f of 2 equals 3, that is a point on the graph of f. So really the only important piece there is position. if I look at the values for the function f prime, that tells me slope. It tells me the slope of the graph of f. Okay. If I look at the function f double prime, remember that discusses concavity of the graph of f. Well, those are all results of differentiation. So when I take derivatives moving forward, that's how I look at that, or I realize that information, because it's all about how things change. Well, if I go backwards through integration, my capital F function can now be defined as the integral of f. Again, that's how I would go backwards, is through integration. So if I choose to define this function as an integral and make one of these accumulation function, that now means that this new guy is all about the area of the original function. So when I pick a value for x, it tells me a stopping point for accumulating the area under the function inside of the integral. So why is that important then? Well, because I can start with an integrally defined function, all of this has been about trying to describe how things change. So if that means starting with an area function is something I can start with, then I need to be able to describe how that area is changing, which means I need to be able to calculate the derivative of this kind of function. So in this case, if g of x is defined as the integral from 2 to x of f of t dt, then by the second fundamental theorem of calculus, g's derivative, g prime, would actually be equal to f of x, which is just another way of explaining this relationship. Going backwards, we use integrals, but if I start with the integrally defined function to go forward to the regular value of f of x, that requires a derivative. So this second fundamental theorem of calculus, this is the final piece in this puzzle. This is the final way that we can link all of these different functions together, and now we can really interpret them in any way that we want to. All right? So let's start by taking a look at an example here. So I'm going to define a function g of x as the integral from 0 to x of the function cosine of t dt. Okay, so first I just want to talk about and explain what the y values of g of x represent. Again, just like with any other function, the way a function works is you pick an input, you plug it in, and then we do some math, and it produces an output. Okay, well, in this case, the math that I have to do is some serious calculus. So in this case, for the function of g of x, okay, our inputs, again, if we think about our ordered pairs, as far as our x's and y's go, so our x's aren't anything special, okay? But in this case, our x value, when I choose that number, this is the stopping point, or the stopping value. So it's where I choose to stop accumulating area under the curve of cosine of t. So then my output, or my y value for the g of x function, that's what they represent. So it represents the area under the function cosine of t, or again, I can actually I don't want to confuse anybody just yet. So let's stick with cosine of t. Under cosine of t on the interval 0 to whatever that value of x is that I chose as my input. So that is what our output values represent in this case, okay? So I first pick my input, my x value. When I have that chosen, then that becomes the end of the interval, and I have to evaluate all of the area from 0 to the end of that interval, and that is the y value for g of x, okay? Now what we want to do is we want to try and find the value of g of x at all these different values of x, okay? So again, g of x is defined as the integral from 0 to x of cosine of t dt. So when I want to find g of 0, that first means what is the integral from 0 to 0 of cosine of t? Well, remember, this was actually one of the properties that we learned about integrals. If I have an integral from a to a, the value is 0. Or in these terms, what that really means is I started at 0, but I haven't moved yet. I haven't moved the second edge of that integral yet, or that area, so there's really no area to accumulate. That's why this first value is 0. Okay? Next one, pi over 6. Well, that means, okay, what is the total area under the curve cosine of t from 0 to pi over 6? That one we can actually do the calculus and evaluate. So let's do that. Integral of cosine is sine. And we're going to go from 0 to pi over 6. Again, because it's t, does not change any of the integration rules. We still carry out fundamental theorem the same way. So I would get sine at pi over 6 minus sine of 0. Sine of pi over 6, pi over 6 is the low-lying angle, so that is the small coordinate. So that's 1/2. Sine at 0 is 0, so we get 1/2. Okay, next one. Let me move up here. G of pi over 4. Okay, so G of pi over 4, same exact idea. So if you really think about it, changing the value of the upper bound does not change the antiderivative. Whoops, we're at pi over 6 again. It doesn't change the antiderivative of the function. So that's still going to turn into sine of t. The only thing that's changing is the upper bound. And again, our a value stays the same the whole time. So this is really just going to be 0 for all of these. So the only thing we really have to worry about is what is sine of our b value that we choose. So this is going to turn into sine of pi over 4 or square root of 2 over 2. Then our next one, g of pi over 3. I'm going to expedite this. If I chose to write all of this stuff out, in the end, it would really turn into what is sine of pi over 3, which is the big y coordinate, so root 3 over 2. Then I would be looking at, I know I ran out of room down here, next one would be g of pi over 2. So again, if I write everything out, I end up with what is sine of pi over 2, and that is 1. So those are the y values for g of x, but again, what they really represent are the total area under the graph of cosine from 0 to whatever that value of x is that I chose to stop at. So let's take, we're going to take a look at Desmos and try to visualize what it is that is going on. So again, what I want you to keep in mind is what we've already talked about here, the idea that g of x is an accumulation function, and its job is to produce the area under the cosine function for certain values of x that we stop at, okay? So here we have the cosine function curve. Now I have it defined as f of x. That name's not super important right now. I'm only using that name to pass it into our g of x function that is integrally defined here, okay? Now I also have a boundary on this guy from 0 to a. A is what I'm using to control as my upper bound, okay? So it works a little bit differently in Desmos. But basically what's going to happen is I'm going to move this slider, and we are going to visually see the representation of our area accumulating. So that blue line, this vertical blue line here, is going to start to move. And as it does, we are going to be accumulating area. Now, another thing to keep in mind, regions that sit above the x-axis will normally produce positive area. Regions below the x-axis will produce negative areas, okay? So let's start moving here. So that is going way too fast. Let's bring it back. Okay. So as this begins, you guys can see, okay, let's pause it right there. So I get to an x value of 1.25. So our total area is 0.949. That is the area of this green region right now. So as that value of x continues to move across that interval, the area is accumulating. So we're gaining more and more area until I get to a value of pi over 2. When we get to a value of pi over 2, that value or that area has come to an x-intercept of the graph of cosine. So what that means is we are about to pass over from positive y values and a positive area region into negative y values and a negative y region. Okay, so because of that, oops, get rid of this extra stuff. Because of that, and it's not going to let me go exactly to pi. Let me do pi over 6 steps. Okay, so right there we are at pi over 2, okay? But now as I pass over, or go past that, now those are all the values that we found already, okay? So we went 0, pi over 6, pi over 4, pi over 3, pi over 2. So those areas are actually those values. Why don't we go back to those? Start at 0 this time, okay? So at 0, at pi over 6.5, that was actually the value that we found here. From 0 to pi over 6, we got 1/2. Now, it's not going to let me do pi over 4 because of the increments here, but when I go to pi over 3, 0.866, that is actually the value of square root of 3 divided by 2. And then when I get to pi over 2, we have a total area of 1. So that region right there under that graph is 1. So all those values that we were just looking at, those are actually the y values for the graph of g of x. Now right now I have the graph of g of x toggled off because I kind of want to reveal that at the end. But in your mind, let's think about what those y values are doing. So we found these first 5 y values. They go 0, 0.5, roughly 0.7-ish, then 0.8-ish, then 1. So it's pretty clear that those y values are increasing right now, which should make sense because the amount of area that I'm accumulating was getting bigger and bigger as I moved across that interval because this was all positive area. Okay? But now what's going to happen, now I'm going to pass pi over 2, and now I'm working down into negative area. So we just went from a total area of 1 back down to square root of 3 over 2, and it's because we just took a little bit of that total area away because now I'm including a negative region. That upper bound has continued to increase, so where I'm stopping the accumulation of the area has moved further down the line. So as this continues, we are going to incorporate more and more negative area until eventually, now I'm at pi. Now those two regions are perfectly equal in size, but one is positive and one is negative, so that's why they actually total up to 0. So what that meant in this section, or this interval from pi over 2 to pi, the graph of g of x would have actually been decreasing because I was including negative area, so I was taking away from everything that had totaled up in that first section, okay? Now, as I continue, now I'm still going to keep decreasing the total area because I'm including more and more negative area to that total. And that process won't stop until I get to, let's see, what is that? 3 pi over 2. So when I get to an x value of 3 pi over 2, I'm done including that negative area, and now I'm going back up to positive y values on this graph, which means now I get to include positive area again. So now this graph will start to increase again. And it's just going to continue that process on and on and on. We can zoom out a little bit. You guys can see, we know the cosine graph is a wave, so it's basically just going to repeat this process over and over and over again. So if you think about all the values that we've seen so far, the biggest area that we've seen anywhere was 1. Okay, let's go back a little ways. Let's see how small of an area we got. So right there, we had a total area of -1 because these first two parts canceled each other out. This was 1, -1, but this guy was also -1. So the smallest total area we ever accumulated was -1. The largest we've accumulated up to this point was +1. And you guys can kind of guess what's going to happen here. It's just going to keep bouncing back and forth between that. It's going to repeat this process over and over and over again. Now, if you take all of that into account, think about all of that, hopefully this next part makes a little bit of sense to us, okay? So this next question asks, find g prime of x, and then find g prime of pi over 2, and then we're going to interpret this result, okay? Well, let me redefine what g of x is equal to. Again, g of x is the integral from 0 to x of cosine of t dt, okay? Just make sure, yes, okay. So by the second fundamental theorem of calculus, the derivative of g prime would require us to take the derivative of this integrally defined expression. And again, because this is just an x, we don't have to worry about the chain rule part here. This derivative just becomes cosine of x. So that x goes in. I can do the chain rule still, but the derivative of x is just 1, so it doesn't actually produce any new factors in the derivative of g prime. So that is the derivative of g of x, and therefore g prime of pi over 2 is whatever cosine of pi over 2 is, and cosine of pi over 2 is 0. So now let's interpret this result, okay? Now first let's talk about g of x. Again, g of x, its job is to calculate the area under cosine of t, okay? And again, that is on the interval from 0 to whatever value of x we choose to stop at. Well then, just by that definition, g prime, remember, every derivative's job is to describe how the previous function changed. So that means g prime's job is the change in area. Oops. Sorry, my tablet's doing that wonky thing again. We would be finding the change in area under the function cosine of t on the interval from 0 to whatever we choose to stop at. So it's the same kind of relationship we've seen in the past with other functions and their derivatives, but now we're referencing this quantity of area. So when I try to interpret the result that g prime of pi over 2 is equal to 0, well, in this context, that actually means that there is no change in area at x equals pi over 2. So when I have reached the value of pi over 2, that means for a split moment in time, that one value, we have stopped changing, which usually indicates that there's a potential for a change in direction. So let's go back to this graph again, and let's revisit pi over 2. So there's pi over 2. Now remember, before that, from 0 to pi over 2, we were increasing. We were accumulating all of that positive area. And at pi over 2, we said this is where we're going to start to cross over into that negative area. So immediately after that, that's when the total area started to decrease, which falls right in line with what we were just talking about. So that is the idea behind the derivative of these integrally defined functions. That's how we can interpret those. They are describing to us the change in the area under the function used inside of that integral. Okay, so now let's talk about the next part, our second derivative. So if I add on one more of these, g prime of x is the change in the change in area, okay? Now, again, with second derivatives, a lot of time we hear phrases like slowing down or speeding up, because a lot of times we think of it as acceleration. We can still kind of do that same thing. So when we talk about the change in area, we're talking about, is it increasing or decreasing? But we can also talk about, is it increasing very slowly, or is it increasing very quickly, or decreasing very quickly, or decreasing very slowly? Well, that has to do with the amount of area being added or subtracted to the total. For example, if I go back to 0, right away, I'm adding in pretty big chunks because the curve is pretty high relative to other parts of this graph. So when I'm near those high points on this graph, you're going to be adding in a lot of area. So in this case, I'm increasing, but I'm doing it pretty quickly. When I get out here towards the low points, this last little chunk that I add in, it goes from 0.86 to just 1. That's not much of an increase, and that's because the curve is pretty low, or close to 0, so it's not going to be totaling up as quickly as it was back at the beginning of this interval. So what we could say around those values as we get closer to pi over 2, we are increasing, but we're going to be slowing down our rate of increase. Okay? So imagine that when we throw the baseball straight up in the air, its position is increasing the whole time, but as we reach that maximum, we start to slow down. That's what's going on here. We are increasing, but we're doing it at a slower and slower rate until we reach that value at pi over 2 where we no longer are increasing. Then after that, okay, we get to pi over 2, we've hit our maximum area for that local area, or that local interval, but then we start to decrease. So we've changed in our directions. So in this case, now we're starting to decrease, but again, right after that, we are decreasing, but we're not doing it very quickly. We only took away a small chunk. But then as we continue to accumulate more negative area, now we're going to start deducting bigger and bigger chunks until we get down near this low area on the graph. That's where it's most negative, so that's where the bigger chunks of negative area are going to be, and so we're going to take away more and more. So now we are decreasing, and we're going to be doing it in a faster rate. After this, now we're going to continue to decrease, but the chunks that we're taking away are going to be smaller and smaller and smaller. So that's the idea of this second derivative for these integral defined functions. It's, again, still that same concept of acceleration, but it's all tied to area, okay? So in this particular scenario, to find g double prime of x, yikes, I don't know what's going on with my tablet. If g prime was cosine of x, then g, got disappearing lines now, g double prime would be the derivative of this, or negative sine of x. So this expression, negative sine of x, is a way to quantify that acceleration, or that change in the rate of change of area. So are we slowing down or speeding up? So in this case, for g double prime at pi over 2, if I were to plug in pi over 2 to this guy, we would get negative 1 times sine of pi over 2, which is 1, or negative 1. So if you think back to our PVA problems, at pi over 2, we have negative acceleration. So in this case, again, if we go back to our graph, let me move this guy back over to pi over 2. We said here that we were increasing that total area, but we were doing it in a slowing down way, slower and slower. And that is indicated by that negative acceleration. So we were increasing, but because that second derivative value is negative, this is like saying that we are slowing down our rate of increase. And in fact, at pi over 2 is exactly where we've reached our maximum. So that all of that ties into play. Now, another way of interpreting it, again, whenever a function is its second derivative is negative, remember that is indicating concave down. So when we look at the graph of g here in a second, because again, just to reiterate, this graph is not the graph of g. This is the graph that g depends on, because we are taking the area of this graph to create the values of g. Remember, I still have the graph of g turned off for the time being, okay? But when we look at the graph of g, we should see at pi over 2 that we should have a relative maximum. We know that because of the zero slope and because of the negative concavity that we just found, okay? So now, one more time. Now we're going to go put all this back together. So now I'm going to turn on the graph of g. So again, what this is going to show, it's going to be a little tricky because the two functions are going to be graphed simultaneously. But as I accumulate area, you're going to see a black curve start to plot itself. Its y values are equivalent to the total accumulated area under this curve that we see plotted up here. So let's do this one step at a time. So pi over 3. So at pi over 3, or excuse me, pi over 6. At pi over 6, the total area accumulated under that graph is 0.5. And if you notice, the y value on this graph is 0.5. Okay, also notice the black graph is increasing on that whole interval, and that's because for that whole window of time from 0 to pi over 6, we were accumulating positive area. Pi over 3, so I've gone 2 jumps, whoops, 2 jumps now. Again, the graph continued to increase because I continued to total up more and more area. Total area is 0.86. That, whoops, where'd it go? There we go. Is also, I don't know why it won't let me get there. Well, if it would let me get there, that y value is 0.866. That's the square root of 3 over 2. So as I continue, and again, when I get to pi over 2, we just said zero slope. It does, in fact, look like this graph is flattening out, okay? And it just reached its maximum. We have negative concavity for sure. And again, that is the idea that this area just reached its peak, because immediately after this, now the total area is going to start to decrease because I'm taking away from the total, because now I'm including that negative region. So now our g of x curve is going to continue to decrease this whole time that I'm adding in more and more negative area. And again, at that point, the total area is back down to 0. That's why the g of x curve now has an x-intercept. So we're going to add in, or excuse me, subtract more from that total because I'm including more and more negative area until I get to 3 pi over 2. And at that point, I've included all of the negative area for that big hump down there. So the total area is at its minimum. So I was decreasing that whole time. I reached that minimum. I bottomed out. But now we're going back on the graph of cosine to positive area. So now I'm going to start to work back towards 0. I'm going to add in more and more of my positive area. And we continue to increase that whole time until we reached a maximum area of 1 again. So this cycle is just going to continue to repeat itself over and over and over again as we go. Now, some of you may be looking at that black graph and it may look familiar to you. That's because that's the graph of sine of x, which should make sense. The integral of f of t, or the integral of cosine, is sine of x. And that's not a coincidence. That is all of these connections just kind of recycling themselves over and over and over again. So there are so many different ways to make these connections, but what this means is that if we define g of x as the area under cosine, then its values are actually the exact same thing as the values of sine of x. That's pretty neat to see that those all kind of come together. Now, what's even cooler is we found the equation for g prime. Well, again, by the second fundamental theorem of calculus, the derivative of g is the exact same graph as the one plotted, which really means whenever this graph has positive y values, the total area will be increasing, which we've already said. And whenever that graph has negative y values, that total area will be decreasing. That is the connection there. That's what that means. Okay? Now, there's one more thing to talk about. Let me get rid of these graphs so there's not extra stuff floating around. With these integrally defined functions, sometimes you will be asked to go backwards. Now, I didn't ask you to do this in here, but I could have asked you for the value of g of negative pi over 3. Well, if I did that, whatever value of x I plug in here needs to go where x is in the integral. So the issue with that, not only that my tablet decided to have a heart attack again, but the issue then becomes, well, my b value, yikes, my b value is now smaller than my a value. Remember, we don't like that. So the way we fix that is by flip-flopping these guys, and we change the sign of our integral. So this really becomes, let me write out everything here properly. This really becomes the opposite of whatever the value from, negative pi over 3 to 0 is. So again, that's just the general rule that whenever we're trying to evaluate these definite integrals, we always have to have a small a to a bigger b value. So if naturally, when we go to set them up, that doesn't occur, we have to fix them with this property. So what that means for us, if we go back to this graph, now I had to remove the restriction that I had on here earlier for this a value. But now what that does is it allows me to go backwards. So normally, this area would be positive because it's sitting above the x-axis. But when we define these integrals and we establish a starting value of 0, anytime that I try to move backwards, everything is the opposite of what it would normally be. So because this was normally going to be positive, now we are deducting it because we have to do that flip and multiply by that -1 out in front. So you're going to see here, when I go backwards, we are going to end up with a negative total area. And so this isn't just going to be for that first section. Again, it's basically just going to work the exact opposite of what it did moving forward. So as I continue to go back, that whole normally positive region will be deducting area. And then as I move down into that lower section of the graph where normally we would be deducting area, we're deducting negative quantities now. So that actually begins adding to that total. And so we could keep going back in that direction as far as we wanted to, and everything's just going to work in that opposite direction. So this isn't a case just because our starting value is at 0. This works for any start value. So for example, if I made this 2, then my starting value would be at x equals positive 2. So anything that I integrate backwards to any value before 2, again, all of that, anything that would be positive becomes negative, anything that would be negative becomes positive because of that reverse direction and the fact that we have to fix our interval to make the order match up and then switch the sign out in front. All right, so there is a lot of content in this section after we've learned first fundamental theorem and second fundamental theorem of calculus. There's all kinds of applications, so hopefully this wasn't too much, but as you guys need to, always come back to the videos to help you as you practice your way through 4.5.